we come to the next presenter, Sergio Vino from Porto.
Porto.
Yes, PhD researcher there in the third year.
Okay, so good morning everyone. Today I'm going to present circular takeoff and landing for motorized kites in airborne wind energy systems. So as we can see by the name, we're going just to think about takeoff and landing for fixed wing kites. It's my table of contents. I'll skip it because we don't have too much time. Starting by the automatic takeoff and landing. Why is so important for a kite or a system, airborne wind energy system, to have automatic takeoff and landing? Because if we want to make it fully autonomous, it has to take off, it has to land. It has to do that when there is no wind or when the weather conditions doesn't allow the kite to fly. So a main solution, I think that is yet to be established, and as you may know, for different kites, there are many different ways to, or many different approaches to, that we can use. Some of them are here highlighted. These are some examples. We have Twin Tech that has a vertical takeoff and landing, Kite that has a rotation arm to rotate the kite and create lift, and Ampix Power that has a linear takeoff and landing, as everyone knows. In our lab, at the Wind Lab, we are from the University of Porto, we have a small-scale prototype. Not the prototype I will talk in the end of this presentation, is another one, a bigger one, and we consider it, we want it to be, to make it part of a ground generation system with a fixed wing, so the kite is a fixed wing. And we were thinking about, since the kite has not a really high wingspan, we were thinking about a new way of taking off that kite, because we already have some simulations without tether, of course, but we always manually take off the kite and manually land. And we were thinking about a way to approach the problem, and we thought, as the title you already saw in the title, is a circular way, or try to do a circular path and take off the kite. But I will explain it more. So these are our 3D motion, or not 3D motion, but aircraft model. We consider the feet as the azimuth angle, beta as the elevation angle, VA as the kite speed, gamma the flight path angle, and theta the pitch angle. And so, starting by considering the equations of motion that for the aircraft in the longitudinal dynamics, we just have like the VA dot, gamma dot, and theta dot. We then, if we want to consider, since the kite is has a tether on its wing, we can have like the motions for the equations for the 3D motion, like the phi dots and beta dots. And with that, we can create a 3D simulation and not just the longitudinal dynamics of the kite. So for the control requirements, so we want to take off the kite, right? And we want to drive it to a steady level of flight. And at that steady level flight, we want to reach a certain elevation angle. So we won't consider the height, but the elevation angle, but we can compute the height, or it depends whatever we want. And also we want to drive the kite to a certain speed, to a certain reference. And of course we want to reach a certain point that the sum of the forces equals 0, so that the kite doesn't accelerate and maintains its elevation and also its speed. This is our control architecture that I'm going to explain later. And so for the speed control, for the speed control we use the simple PID controller just to gain velocity or to control the velocity of the kite by computing the error of the speed and then applying a simple PID controller to adjust the propeller force of the kite. So we have, as we saw, I think that I forgot to mention, we have as control inputs. At this stage, we are considering the propeller force and the pitch rate. So at this stage, we're not controlling exactly the elevation deflection angle, okay? In the future stage, we will consider, of course, because if we want to apply in a small prototype, we want to control the elevator, of course. So we already have the speed control and now the elevation angle control. And here we thought on using a sliding mode control, okay? And it is possible to control the elevation angle of the kite by adjusting, okay, the pitch rate. That's the other control variable. If we consider the tracking error of the elevation angle, we can define a time-varying surface in the state space X. And then we obtain a time-varying surface SD as we show here below. We also define the pitch rate control law as Q equals to minus Ts, a function set of X, where this function is here defined to reduce the shattering of the control, okay? Because we don't want to always, when we are close to the surface of this surface, we don't want to always have shattering of the control, and so we define this function that is equals on if we are in a certain part of the surface. If we are within a certain boundary eta, we consider exactly the surface that we are, and if we are in the other way, it's exactly the other way. So the parameter Ps of the control law is the convergence rate to the surface. Lambda that we saw previously here is the convergence rate within the sliding surface to the desired point, and eta is the boundary layer that satisfies the sliding condition. We also done some stability analysis, and the Ks that we used in the simulations satisfies the stability condition for all state X. So for simulation, as I said, we have two control requirements: the kite speed and the elevation angle that we want to reach in the takeoff stage. These are some control gains and parameters and simulation parameters. So, as you can see, the mass and the area is really is not that big. Okay, we are starting with a really small scale prototype with a wingspan of 50 centimeters, so it's really small. We want to test it in our lab, and it's a mathematics lab, so it's not that big. We don't have that many resources, and we want to test it so that we can go a step further and maybe try in a bigger prototype. So these are the results. We thought in first control the kite in order to reach a certain speed, a certain reference, and when we reach that speed, we control the pitch rate in order to start gaining altitude, maintaining the speed. So the control variable for the speed was the propeller force, and there it is at the right, and the kite speed at the left. So the reference was a ramp in order to achieve 10 meters per second. The kite can actually follow the reference. And for the elevation angle, after we reach the 10 meters per second of speed, the kite starts to elevate. This is the pitch rate. And so we would think that it's just in the vertical plane, but as I told you, we tried to do like a 3D motion, and so this is our result. So the kite starts to, I don't know if I have a pointer, yeah. So the kite starts to gain velocity, okay, and at a certain point, when you reach 10 meters per second, it starts elevating until a certain desired elevation angle. As you can see, this sphere, we have a motion of like a sphere because the feather length is always the same, and while we are taking off, the feather is pointing to the center of the sphere, okay, and we are like doing this motion, okay. That's why the flight radius is starting to decrease, okay. In the future work, we might think in a way of adjusting the kite in order to like take off and maintain the radius of that circle. We have some ideas, maybe in the next conference we have the results for that. This is our small scale, it's really small, and we were thinking about using really simple and fast prototyping to do this, to test this controller in our lab. Okay. So for the conclusion of future work, so as I told you, ATOL is mandatory for a system to be commercialized and wherever to use it. Several approaches of automatic takeoff and landing exist, and I think that the circular takeoff and landing or rotational takeoff and landing is the least used. And so that's why we are thinking in trying to innovate in that way. For future work, we want to finish the small scale, we want to test it in real life, and we also want, as I told you, develop the transition phase. So we are thinking about this takeoff to reach a certain point and then transition it to the production phase or whatever. Yeah, I think that's it. I don't know if you have any questions, so I'm open to.
Thank you, Sergio. Are there any questions? Is there a question?
Hi, thank you, Christian from Airborne Wind Europe. I just want to know if you are in contact with Enerkite because they do this rotational thing.
Yeah, so we don't have exactly any contact with them, but their concept is slightly different from ours. So their kite is a soft kite, okay, and the tether is attached in the lower part of the wing. And now we are considered the tether attached to the wing, okay. So imagine this as the Enerkite wing. The feather in Enerkite is attached here, and it starts gaining velocity in the arm like this, right?
They have two tethers. They have the control from the posterior.
Yeah, but they start rotating like this, and we are thinking about starting rotating like this. So we are a fixed wing and start rotating like this. And what is happening in the simulation is that when we gain altitude, the kite does this, right? And we need to think in a way of not doing this, but do like this, so, with a feather in the wing or whatever. We have some ideas.
The concept that you mentioned
is similar to the Sherbini's work a couple of years ago. Yeah.
And I think in the 80s or 90s there was a sport.
Where it's called
flying around.
Control line flight or something like that, where we have two tethers, and one is to control the elevator of the plane. And so I'm not sure if they have like a motor or a rotor or not, propeller. Yeah, they have a propeller, and then you have two lines that control the elevator of the plane, and you simply just with the differential length of the feather, you control the elevator. That's almost what we are trying to do, but a different way.
Thank you.
As I said, we are a mathematics lab, and we are trying to get hands-on in real things. So, yeah.
Thank you again, Sergio.
Thank you.